Hi everyone, this is section 6.2 on properties of the sets. So first, now that we establish once again all the important things about sets and all the conditions, then we want to work on a set of identities that we actually might want to prove. So sets identities are going to be equation that involve sets in situations that are true for all sets. We want to study them because they can simplify complex set expression, prove relationship between sets. They're the foundation for Boolean algebra and logic circuits, and they're used in database query optimization, which is something that you're probably going to need to do on certain areas of your IT majors. They use also parallel structure to logical equivalence. So there's a lot that we can do in the same way that we do with logic with sets. We're going to have things like Morgan's laws, like distributions, set identities, all those kind of things. So now let's introduce the basic set of identities. We have the identity laws. For example, if we take a set and we make a union with the empty set, that's just going to give me, again, the set. And if we make an intersection with the universe of the context that we're using, then we're going to get back our original set. The domination laws is, of course, what dominates between empty and the universe for a set. So, for example, if we make a union with the universe is just going to eat the set because it's part of it. And so we're going to get the universe back. So A union the universe is just going to give me the universe. Now, in terms of interception, if I intercept anything with the empty set, it's just going to give me the empty set because the empty set has no elements. So the intersection is, of course, no elements. Now, in terms of other type of law, we have the idempotent laws. So, for example, if we make a union with the set, with itself, then we're going to get back the set. And if we make an intersection of a set with itself, then we're going to get back our original set. Now, the complement laws are different. Like if I make a union of a set with the complement, then of course we're going to get the universe, and the complement set is disjoint with the original set. So if you make an intersection between A and their complement, obviously they're not going to have elements in common, and the intersection is going to be empty. Now, we have operational laws like commutative, like for example, A union B is the same that B union A, and the same A intersection B is the same as B intersection A. The order doesn't matter in union or intersection. We also have association laws where it doesn't matter what starts first for union or intersection. You can do A union B union C, and it's going to be the same that if you do first B union C and then union A. And same with the intersection. A intersection B, then intersection C is the same that first do B intersection C and then do intersection A. Grouping doesn't matter, and we can write this in any unambiguous way. Now, we also have distribution laws, and these do change a little bit. These are some of the ones that we need to pay attention. If we're distributing a union over an intersection, then we're going to get the union of the first set with the second set intersected the first set union the third set. Okay. Similarly, if we distribute the intersection, if we're distributing the intersection is A intersected B union C, we're going to get A intersected B union A intersection C. This is going to be helpful to sometimes split some of the intersection, and it's very useful to work with surveys and things like that where we want to check for particular intersection of certain sets. The key pattern here is that union distributes over intersection and intersection distributes over the union as well. This is similar to the arithmetic, of course. That's why it's called distribution. where we multiply A over B plus C, and we get A times B plus A times C. But in this case, both operations do distribution in set theory. Now, the De Morgan's law here, they have to do with the complement. So, for example, we have the complement of A union B. That's going to be equivalent to the intersection of the complement of A with the complement of B. Or the complement of a union is the intersection of the complements. On the other hand, if we have A intersection B and we do the complement, that's actually equivalent to the union of the complement of A and B. Now, when you negate a complement, what's happening is that you're changing unions for intersections or intersection for unions. And of course, we do complement of each set. This is very similar to the logic Morgan's law, where we're negating proposition, and so it flips the in and the or. And of course, if you're curious, of course, intersection is in and union is or. So it kind of makes sense to use the Morgan laws in here. And the complement is kind of tied to the idea of negation, or it's like the other set of elements from what we have with logic. So there are a exact parallel to what we have with Morgan's laws in logic. Now, we also have assertion laws. If we have a smaller set and you do a union, then of course the bigger set is going to absorb. And so if we do union of A, union A inter B, that's just going to be A, because A inter B is a smaller subset of A. And if we do A intersection A union B, of course, the bigger set here is going to be A union B, but because we're doing intersection with A, then we get A back. Now, do you know that why these are going to be true? Well, for the A union A intersection B, we have that the element of A intersection B are already in A, so you're adding them doesn't change a lot. And for the intersection of A with A union B, the idea is kind of backwards. The element of A union B includes already all elements of A, so intersecting just give me back the original set. Now, the double complement law is, of course, the complement of the complement is just the set. The universal set and empty set complements are going to be each other. So the complement of the universal is the empty, and the empty complement is the universe. Now, we can also see the difference as intersection. So we can see the difference as A intersected B complement. And so this is going to connect the set different to intersection and complement in this way. Now, notice all these identities that we're doing is something that we can probably prove now. We can prove that these equalities are going to be true. Now, if you want to prove set identities, there's two main methods. The method number one is the element argument, where you show that an arbitrary element is in the left side, if and only if it's in the right side. And this is going to use logical equivalences and definitions. The method two is subset argument. You prove the left side is a subset of the right side, and then you prove that the right side is a subset of the left side, and then you conclude that they're equal. Okay? So you can pretty much kind of argue that the method one can convert in the method two, but with the method one, you're going with an if and only if relationship, so you're kind of proving both at the same time. Now, there's, of course, a method number three, which is using identities. You apply identities that we already know, and you do algebraic manipulation to get to what you want. Now, for example, let's prove that A intersection B union C is equals A inter B union A inter C. So let's pick an arbitrary element. So if we pick an element of A inter B union C, then by definition, X belongs to A, and X belongs to union C, because this is an intersection, right? So it needs to happen both. Now, from X belonging to B union C, that means that X belongs to B or X belongs to C. But now we can use the distribution of this N, and we can separate this to be equivalent to X belongs to A and X belongs to B, or X belongs to A and X belongs to C. Hence, then X is going to belong to the intersection of A and B, or is going to belong to the intersection of A and C. And this or in the middle is just a union, so we can say that X belongs to A inter B union A inter C. So since X was arbitrary, then the sets are going to be equal. And notice that we're maintaining this equality all the time. Now, the key here is that we're using the distributive law from logic. Now, let's see another way. Let's see the method of proving with sets. So let's prove that A union A inter B is equals A. We want to show that A is a subset of A union A inter B. The way to show that, of course, to prove that something is a subset, then I need to show that if I have an element on one side, it's going to be on the other side. But in this case, it's easy, because if X belongs to A, then by definition of union, X is going to belong to A union A inter B. It already belongs to one of them. The part 2 will be proven that A union A inter B is a subset of A. But we do the same thing. We pick an element that belongs on A union A inter B, then we break it apart. Case number 1, if X belongs to A, then we're done. We show that it's a subset of A. Now, if X belongs to A intersection B, then by definition of intersection, X belongs to both A and B. So that means that X needs to belong to A. So by definition of intersection, in either way, X is going to belong to A. So we just showed that this set was a subset of this. Hence, since I proved both sides, both subset relationship, then I can have that A union A inter B is just A. Now, let's do another example with properties. Well, let's simplify A intersection A complement union B. Here is about using the laws that we already know. So for example, if I have A intersection A complement union B, I'm going to use distributive law. And so I'm going to go A intersection A complement union A intersection B. So I use the distributive law. Now, by the complement law, A intersected A complement is empty. There's nothing in there. There's nothing common. And so we're only going to get that this is empty union A inter B. But by the identity law, this is just going to be A inter B. And so we're done. This is my maximum simplification. I cannot get further than this. Now, we can also do something like simplify A union B intersected A union B complement. And here we want to go backwards in the distribution. Notice this is A union B intersected A union B complement. So I can just make it so this is A union B intersected B complement. But once again, this is just going to be the empty set. And this is A union empty, which is going to give me A. So this is the identity law. All right. So now let's talk about Venn diagrams. Venn diagrams are important for showcasing relationships of 2 or more sets that we might need in a situation. Venn diagrams visualize the set relationships, and their basic use are show relationship between sets, or check the set operations, or understand set identities, and check if an identity might be true. With Venn diagrams, we can suggest that an identity is true, show that the identity is false by counterexample, but they cannot really prove that an identity is going to be true. This only shows specific examples. For example, A union B, which is everything in A or B or both, is given by this Venn diagram. We just set the universe in this rectangle. Then we do two sets with intersection. And then A union B is just going to be all the color pieces. Now, intersection B is what is in both A and B. So, of course, it's going to be the common elements between A and B. We have A minus B, which is what is in A, but it's not in B. And so we have that all the elements here in the shade regions represent A, but we remove the intersection with B. We remove the common elements with B. Then the A complement, of course, the last operation is if we have a set A complement is everything outside of A. If we have more sets intersecting with A, then we just got to be careful that we're not including anything that is in A. Now let's talk about applications of this. Here we have a parallel between set theory and logic. For example, in set theory, we use the union. In logic, we use the or. And the intersection is the and. The complement is the not. The universal set is like a tautology, and the empty set is like a contradiction. There's a parallel between them. The subset is somehow an implication, and the equality is going to mean some sort of equivalence here in logical terms. So this is why there's a lot of parallels between set theory and logic, and they use some of the symbology. And for example, for proving things with union, you're gonna come with the or statements, and for proving intersection, a lot of the and statements are gonna be there. For proving complement, you want to show elements that are not in the set, so that's why they have so much parallelism when you're trying to address statements with set theory. Now, set operations are going to be fundamental for things like database and SQL. For example, you can take the A being the students taking math, and B, the students taking computer science. So the A union B is going to be the students taking math or computer science, or both. So notice that this is something like select from students where the major is either math or computer science. This is kind of statement shows how it works in one type of query. Queries of intersection. A student taking both math and computer science. So you'll use select from students where taking math and taking computer science. So you can see that a lot of the conditions in set, they come on the where part, which is where you usually set conditions. Now, the subtraction also come into place there. If we have A minus B, you have the students taking math but not taking computer science. So you select from the students where the major is math and not where the major is going to be computer science. Okay, so in summary, we have a bunch of different laws that we introduce. We might have to prove some of this on the exercises. Set identities, you got to remember that are equations that are true for all sets. We have things like Morgan laws here with complement changing the union to the intersections. And you have three methods for proving identities: the element argument with if and only if, the subset argument with both directions, and using known identities to prove those. Now, Venn diagrams are going to help me visualize things, but they don't necessarily prove anything. They can work as counterexample, but never as proof. And there's a lot of parallel in logic with the symbology that we have in sets to logic. Once again, the common mistakes to avoid is thinking that Venn diagrams will work as proof. And you want to be very careful when you're using your Morgan's law about not changing operations. The complement changes operations from union to intersection and from intersection to union as well. You want to be careful when applying distribution, both U and union and intersection, distribute and set theory. And you want to be careful not to confuse A minus B with B minus A. The order is going to matter here a lot. So the next chapter is going to talk about function and relations. But in the meantime, let's take a look at some examples of how to operate with sets and what kind of things we can prove.